Okay, so we're back and we're going to talk more about equilibrium today. So far you guys have learned how to write the equilibrium expression or the law of mass action. You have learned how to write the reaction quotient. You have learned how to manipulate the reaction, that law of mass action, if we have a series of reactions or if we reverse the reaction or if we multiply by a coefficient. So today we're going to work on applying that law of mass action or that equilibrium constant expression, and we're going to learn how to use it to calculate concentrations at equilibrium, and we're also going to learn how to use concentrations at equilibrium to calculate the equilibrium constant. So we're going to be able to go back and forth, and that's just algebra, but we're going to talk about the chemistry. So let's go ahead and jump in to our PowerPoint here. So as I said, what we're doing today is applying K, applying that equilibrium expression constant. So we're just going to jump right in and we're going to use an example as our teaching tool here as we go through this process. So if we were to consider this reaction, this is the reaction between water and carbon monoxide to form hydrogen gas and carbon dioxide. And we're given that the K is 2 at whatever temperature at which this equation is taking place. So if we assume that we start with 8 molecules of water and 6 molecules of carbon monoxide, and it's asking us how many molecules of each of our chemical species are going to be present at equilibrium. So we're going to use a tool today called an ICE table. And this is really a critical problem-solving technique for equilibrium problems, both this unit and next unit as we get into acids and bases. So we're going to get very, very familiar with ICE tables. So our first step, anytime we're going to be solving for equilibrium concentration, is to write that law of mass action or that equilibrium constant expression. So we would write that K is equal to the concentration of hydrogen times the concentration of carbon dioxide divided by the product of concentration of water times concentration of carbon monoxide. And it is important to point out that this is the concentration of water vapor. This is a gas. It does get included in that equilibrium constant expression. Normally, we would do this with concentrations or pressures. Since everything is at a 1-to-1 ratio, we're able to, in this problem, actually work with number of molecules, number of moles. If we didn't have the same number of reactants and products, we wouldn't be able to do that, and we would need to convert to molarity or to pressure. But in this case, this works out for us. So we've written our equilibrium constant expression. Now we're going to ICE our problem. So ICE stands for initial, change, and equilibrium. So every time we do this, we're going to set up a table. I usually set it up underneath my equation so that I have those headers so I know what I'm talking about in each of my columns. So initially, I know that I have 8 molecules of water and 6 molecules of carbon monoxide, and I have no hydrogen and no carbon dioxide. Now, when it comes to this change row, we know that these are all 1-to-1. So whatever the water changes by, and the water is going to lose concentration or lose molecules, the carbon monoxide is going to change by that same amount. And again, because they're 1-to-1 ratios, the hydrogen and the carbon dioxide are going to increase by that same amount. And since we know we're going to be doing some algebra, we're going to go ahead and use X here. So we're going to say that water and carbon monoxide are both going to go down by X, and hydrogen and carbon dioxide are both going to go up by X. So we have 2 minus X's and 2 plus X's. So at equilibrium, that means that we're going to have initial plus change, which means that our concentration of water at equilibrium is going to be 8 minus X, carbon monoxide is 6 minus X, and hydrogen and carbon dioxide are both going to be X. So we've set up our ICE table. We've filled out all of the rows and columns in our ICE table. Now we're going to plug these values into our equation and we're going to solve. So at equilibrium, we're going to take these values at equilibrium. We're going to plug them into that equilibrium constant expression with the K value of 2 that we were given. And now we're going to solve. And as you guys can see, this is going to give us a lovely quadratic equation that we have to solve for. If you put this into your graphing calculator, it will give you 2 answers. One of those answers is going to be 24, I believe. Yep, 24, 96 times 4, 24. And the other one is going to be 4. And we'll talk about how you decide which of those values is correct in just a second. Well, actually, we can go ahead and talk about it now. You can see that x is 8 minus x. If x is 24, we can't have negative molecules of a gas. And so we can rule out 24 because it doesn't make sense. In the same way, if we got an x value that was negative, that wouldn't make sense. So we can rule out any values that don't make sense. And so then that gives us that the answer here is 4. And we're almost done. We now know what x is, but we want to know what the concentrations are at equilibrium. So we need to plug this x back into these little equations and find that at equilibrium, there are 4 molecules of water, 2 molecules of carbon monoxide, and then 4 molecules each of hydrogen and carbon dioxide. So pretty simple algebraic manipulations here. Okay, we're going to work through a problem that approaches it from the other direction of being given some initial concentrations and some equilibrium concentrations, and we're being asked to find K. So in this problem, we have a closed system. It contains 1 times 10 to the negative third molar hydrogen and 2 times 10 to the negative third molar iodine at 448 degrees Celsius, and we allow it to reach equilibrium. We analyze the equilibrium mixture and we find the concentration of hydrogen iodide, and it asks us to calculate the K for this reaction. And then it gives us the reaction. 1 mole of hydrogen reacts with 1 mole of iodine to give us 2 moles of hydrogen iodide gas. So anytime we have an equilibrium problem and we have a change, we want to figure out concentrations or we want to figure out K, we're going to go ahead and ice it. So here's our ice table. We have our hydrogen concentration and our iodine concentration initially. We know that we have no hydrogen iodide initially. And we know what the hydrogen iodide's concentration is at equilibrium. It says 1.87 times 10 to the negative third molar. So we know what the change is here. The change in hydrogen iodide is a positive 1.87 times 10 to the negative third. So we would put that in here. Now, we know also from stoichiometry that for every 2 moles of hydrogen iodide that appear, 1 mole of iodine disappears. And so we can figure out that these 2 numbers, these changes, should be half of this change and should have an opposite sign. And so we figure out that that means that these change by negative 9.35 times 10 to the negative fourth. And now we're able to calculate those concentrations at equilibrium by subtracting the change from the initial. And so at equilibrium, we now have 3 concentrations. And now that we know the concentration of all 3 at equilibrium, we can plug that into the equilibrium constant expression, which is the hydrogen iodide concentration squared divided by the product of the hydrogen and the iodine concentration, D1. So approaching the problem from a different perspective, still the same process. All right, we want to talk about one more example, and that's one where our equilibrium system, where we're going to make something that we call a simplifying assumption. So we're going to take a look at this exercise. It tells us that 2 moles of bromine are placed in a 2-liter flask. So with 2 moles in 2 liters, we know that we have a 1 molar concentration at 1,756 Kelvin, which has enough energy to split apart some of the molecules. So it asks us if the equilibrium constant is 4 times 10 to the negative fourth at this temperature. What are the equilibrium concentrations of the bromine molecules and atoms? So once again, we're going to ice this problem. So I'm going to stop sharing and we'll move to the board to take on this problem. So we know that we have bromine, and our diatomic bromine in its gas state is being broken apart into 2 bromine atoms. And so we are going to set up an ice table. Okay, so our initial concentration of bromine we know is 1.0 molar. And we know that our initial concentration of the bromine is 0. Now, we also know that this is going to go down by x. And for every one of these that breaks up, I get 2 of these. So this is going to increase by 2x. Okay. So this is initial. And it is going to change by this. And this means that at equilibrium, this is going to be 1.0 minus x. And this is going to be 2x. Let's hold that thought for a moment. We're going to write our K expression. Our K expression is going to be the monatomic bromine squared divided by the concentration of bromine. Now, we were given a K value here, and our K value was 4 times 10 to the negative fourth. So we're told that this equals 4.0 times 10 to the negative fourth. Now, as you guys saw with the first problem, solving these can get messy. We have to deal with quadratic equations. There is a simplifying assumption. So we know that this is 1.0 minus x, but we also can see that this equilibrium constant is really, really small. So that means that this x value is probably also going to be very, very small. In fact, it just might be small enough that with consideration of significant figures, we might not see its impact here. This might still be, with significant figures, 1. So we're going to make the simplifying assumption that it is. Okay, so instead of saying 1 minus x, we're going to say it's approximately 1.0. And we're going to double check ourselves when we're done, and we're going to make sure that that simplifying assumption was okay. So let's go ahead and plug into this equation, okay? And so we have 2x here. So we have 2x squared. Oops, I'm going to have to move this up, aren't I? All right, so we're going to go ahead and plug in. So we have 2x squared, because that value is 2x. It's not x, it's 2x. So we have 2x squared divided by 1 equals 4 times 10 to the negative fourth. And so I have that 4 times 10 to the negative fourth is equal to 4x squared. So I have 1 times 10 to the negative fourth, 1.0 times 10 to the negative fourth is equal to x squared. So that means that x is equal to 1.0 times 10 to the negative second. There we go, 1.0 times 10 to the negative second. So let's go back to our simplifying assumption. This is 1.0 minus x. If x is 1.0 times 10 to the negative second, that means that this value should be 1.0 minus 0.01. And our significant figure rules tell us that 1.0 minus 0.01 is 1.0, because I have to ignore that 1, because I don't have anything to subtract it from up here. And so we know that our simplifying assumption in this case gives us a number that is valid. So now we're going to go back and we're going to plug in to find our values at equilibrium. I'm going to leave our X down here. Okay, so at equilibrium, our concentration of bromine is 2.0 times 10 to the negative second, and our concentration of diatomic bromine is still 1.0 molar. And that's how we use the simplifying assumption. And we'll use that a lot as we go through this unit and as we go through the acids and bases unit and the equilibrium portions of that. So I hope this is helpful. As always, if you have any questions, let me know.